Let's begin with Chapter 10, the t-test for two independent samples. Last time we went over the single sample t-test, where we compared the sample mean with the population mean to get the t-statistic. However, if you think about it, most behavioral science research is less designed to compare the population mean to the mean of a sample, and instead most often research involves comparing two sample means to another. And the main reason for this is that, first of all, most of the time we don't have the mean of the population, and second, many researchers use a control group in their research. So using this test, we can compare the mean of the research sample with the mean of the control sample. A lot of times you want to see if two groups are different. So for example, let's say we want to know if dog owners who live in the country spend more time walking their dog than dog owners who live in the city. So our sample would be dog owners that live in the city and dog owners who live in the country. So clearly those are two independent samples, right? The samples are not related. The group of people that own dogs that live in the city are completely different than the ones that live in rural areas. And that's why we would use a t-test for two independent samples. After this chapter, you will be able to understand the structure of research study that's appropriate for independent measure t-hypothesis tests, so meaning when would you use an independent measure t-test versus the other ones that we are talking about. You will be able to test differences between two populations or two treatments using independent measure t-statistics. You will be able to evaluate the magnitude of the observed mean difference, so again, effect size, by using Cohen's d or also r squared. And again, we're going to be using our confidence interval. And lastly, you will be able to evaluate the assumptions underlying this test and how to adjust calculations when needed. You can see there's a lot of similarity to the last chapter. It's just really that now we have two independent samples. That's the difference. So what do you think the null hypothesis is for independent measure tests? The same idea as before applies. Basically, it's just now we have two samples, right? Talking about two populations. The null hypothesis is that the mean of the first population equals the mean of the second population, because that means there is no difference between the two, right? If the mean of the first one is the same as the mean of the second, then there is no difference. Or you could also say that the mean of population 1 minus the mean of population 2 is 0, because if they both are the same, then it would equal 0. How about the alternative hypothesis? Remember, that's the one that just states there is a difference. And again, this is what this would look like. Population mean 1 does not equal population mean 2, because that means they are different. Or you could say the population mean 1 minus population mean 2 does not equal 0, because again, that means they are different. Only if they are the same, they would equal 0, and then that would be the null hypothesis. The basic idea and calculations are very similar to what we have seen for the single sample t-test last week. So remember, this is the formula we had for the t-test. The sample mean minus the population mean over the estimated standard error. But now remember, we are dealing with two separate samples and two separate hypotheses about two different populations. So the basic structure of the t-statistic for independent samples is now we have to consider the mean for both samples, the population means of the hypothesis that there is no difference, and then also the standard error, again now for two samples. So the T formula for the independent measure hypothesis test reads sample statistic minus hypothesized population parameter divided by the estimated standard error. And remember, the population mean is always based on the hypothesis that there is no difference. So that part will always equal 0. The same goes for the estimated standard error, since now we have to consider this for two different samples. So last time we said that in the single sample t formula, the standard error measures the amount of error that's expected for the one sample mean that we had. For the independent sample t-test, the standard error measures the amount of error that is expected when we use the sample mean difference of M1 and M2 to represent a population mean difference. So M1 approximates population mean 1 with some error, and M2 approximates the population 2 mean with some error. Since we want to know the total amount of error for our two samples to estimate our two population means, we add the two errors together and then end up with this formula. Important to remember is that this equation shows the standard error concept, but it is unbiased only if N1 equals N2. So basically both samples have to be the same size. But what if we have two samples for which the number of respondents are different, so N is different, so N1 does not equal N2? In this case, we need to put different weight on the two sample variances. Remember that the variance we get from a large sample is more accurate to estimate the population variance compared to the smaller samples. So therefore, when you have two different sample sizes, the larger one is going to be more accurate. In order to correct for this problem with two different sample sizes, we can use what's called a pooled variance, in which each carries its weight according to the sample size. Remember that when we calculate the variance, we divided the degree of freedom by the sum of squares. When we pool them together for two samples, we add the sum of squares for both samples and divide them by the degree of freedom for both samples. Remember, degree of freedom is n minus 1. So n here determines the different weight. Let me give you an example for the variance and the pooled variance. Let's say we have one sample that has a sum of square of 70 and a second sample that has a sum of square of 42. And let's assume in both samples we had n equals 8. So for this one we're going to find the variance and then calculate the pooled variance. And I want to show you, because they have the same number of people, that both variances count the same weight. So for the first sample, if we get our variance, it's just the sum of square over the degree of freedom. So for the first sample, this is going to be 70 over 7, because remember we have 8 people, degree of freedom is n minus 1. So the variance for the first sample is 10. We're going to do exactly the same thing for the second sample. So here we get the sum of square of 42 over the degree of freedom 7, so we get a variance of 6. These are the individual variances for both samples. Now let's pool them together. So by formula, this is the sum of square 1 plus the sum of square 2 over the degree of freedom 1 plus the degree of freedom 2. So that's 70 plus 42 over 7 plus 7, which is 112. Divided by 14, so the pooled variance is 8. So let's see what this looks like on a distribution. So let's say this is our distribution. We had the variance for the first one is 10, so that would be located right here. The variance for the second sample is 6, so that would be located over here. When we pool them together, the variance is 8, which is exactly halfway between the first sample and the second sample. Now let me show you with B how sample size matters. So again, we have a sample that has the sum of square of 70 and the second sample sum of square of 42, so that didn't change. But now assume that the first sample has an n of 8 and the second sample has an n of 4. Again, calculate the two sample variances and the pooled variance. We start by getting the variance for the first sample. Again, we have 70 over 7 equals 10, because nothing changed, right? We still have the n equals 8. But for the second sample, now we have 42 over 3. So the variance for the second sample is 14. These are the individual variances. Now we get the pooled variance. In this case, that's 70 plus 42 over 7 plus 3. And that is a pooled variance of 11.2. So now again, let's look where this is located. Where is the pooled variance located? The variance for the first one we said is 10. The variance for the second sample is 14. and the pooled one is 11.2. So you can see it's closer to the one with a variance of 10. And that's because we have an n of 8 for the first sample. So the variance of this one weighs more. It pulls it over, right, to the sample with the higher number of people in it. So the larger sample weighs more. The degrees of freedom for the independent measures t-statistic are determined by the degree of freedom values for the two separate samples. So the degree of freedom for t-statistic is the degree of freedom for the first sample plus the degree of freedom for the second sample. And you can rewrite the formula again to read n1 plus n2 minus 2. So the number of people in the first sample plus the number of people in the second sample minus 2. Whichever is easier to remember. These are the two important formulas for the independent measure hypothesis test. One is our estimated standard error one, and we can just use the pooled variance. This way you never make a mistake. Doesn't matter if what your n is. And then also our t-statistic. Once we have our t-value, we are now at the same spot we were with our single sample test. We now know with the hypothesis test if our finding is significant. So depending on our t, was it big enough to be in the critical region? If our calculated t is in the critical area, again we can reject the null hypothesis and now have to determine again the actual size of the effect. And again, in order to measure effect size, we just calculate the estimated covariance d or the percentage of variance explained. For the estimated covariance d with the two samples, we take the estimated mean difference over the estimated standard deviation. And remember that covariance d, the size of the effect was explained on page 232. So the larger the d is, the closer it is to 1, the larger the effect is. Or we can calculate our R squared, which is the percentage of variance explained by the treatment. The variability accounted for over the total variability. For a step-by-step example of a t-test for independent samples, please check out the video I posted separately called Dog Behavior. Check it out. When we looked at the confidence intervals for estimating the population mean last time, we estimated the population mean from the sample mean by calculating an interval where we can confidently say that our population mean should be. We did this by the mean plus minus t times the estimated standard error of the means. But now we are talking about two samples. Now for two samples, we still have to get our t first. Everything else we get from our sample data. So the mean for the first one and the mean for the second one and the estimated standard error of the mean. Then we can calculate the estimated value for population mean 1 minus population mean 2. So the sample mean should be relatively near to the population mean, because the confidence interval is a range of values where the population mean, the value of the parameter, should be located. So how would we report our findings? In the literature, you would report whether the difference between the two groups was significant or not. Then you would report the descriptive statistics, so usually your mean and your standard deviation for each of the two groups. You report your t-statistic and your degree of freedom, and you also report the p-value and the confidence interval. So let me show you what this would look like. So let's say we found that the difference between the sample mean systolic blood pressure in diabetics and non-diabetics was 6 millimeters mercury with a 95% confidence interval from 1.1 to 10.9 millimeters mercury. The t-test statistic was 2.4 with a 198 degree of freedom and an associated p-value of 0.02. So you report this in one sentence. You say the mean is 6 millimeters mercury, 95% confidence interval ranging from 1.1 to 10.9. Your t is 2.4, degree of freedom 198, and your p-value is 0.02. Just like before, for these type of t-tests, we can also have directional hypothesis and one-tailed tests. So you use directional tests only when predicting a specified direction of the difference is justified. So for example, if we use our dog behavior example, if we're saying that because of pad of the head, the dogs are going to sit longer, then we would expect our findings to be in the critical region to the right. If we would say something is lesser, right? So for example, the dog sitting less time, then we would expect our findings to be in the critical region to the left. So we have to locate the critical region in the appropriate tail. And we have to report the use of a one-tailed test explicitly in the research report. So you also write, is it a two-tailed test or a one-tailed test? There are certain assumptions we make for the independent measure t-test. First off, the observation within each sample must be independent of each other. The two populations from which the samples are selected must be normal, and also the two populations from which the samples are selected must have equal variances. So that means homogeneity of variance. But how do we know if the two samples have equal variance or that there is homogeneity of variance? For that, we use the Hartley's F-max test that considers the variances of both samples. If the two population variances are equal, then the two sample variances should be very similar. When the two sample variances are close, we can be confident that the homogeneity assumption has been satisfied and we can proceed with the test. But if one sample variance is more than 3 or 4 times larger than the other, then we need to be concerned. Large value indicates a large difference between sample variances. So a small value, usually near 1, indicates a very similar sample variance. Please look at table B3 on page 576, because here you can see we're going to need k and n minus 1 for that. N minus 1, again, not a problem, because that's the number of people, and k is just the number of samples. If your calculated t-value is smaller than the critical F-max value, you can conclude that the data do not provide evidence that the homogeneity of variance assumption has been violated. In summary, for the independent t-test statistic for hypothesis testing, we again have our 4 steps. We start raising the question, what kind of t-test is needed? What kind of scenario do I have? Are the samples independent? Are the samples correlated, which is going to be the next chapter we'll talk about, or do I have a single sample t-test? Once you decided what t-test to use, you state the null and the alternative hypotheses and you select an alpha level. Step 2, you locate the critical region using the t-distribution table and the degree of freedom. Then you calculate the t-test statistic, and then you make a decision regarding the null hypothesis. Congratulations, you reached the end of this chapter. Remember, if you have any questions, please email me anytime. Bye. See you next time.